This presentation will discuss the process and product design of a coffee stout by the Deja Brew Brewing Company. The team for this design includes Shannon Griffin, Nicholas Adams, Ferris Hawari, Robert Scott Core, and Rebecca Stepp. Here is an outline of what is to be covered throughout this presentation. This includes an overview of the market, a process overview, economics, safety, and a product overview. The task we are given is to design a brewing process that produces a coffee-flavored beer. The brewery is located in Tampa, Florida, with a production goal of 7,830 barrels of product per year. The overall equipment cost for this process is $700,000 with a total capital investment of $5.6 million. The net present worth was determined to be $1.3 million. The beer that is being produced is a stout, which is made using roasted malts. The final product will contain around 7.7% alcohol by volume, and the coffee flavor will be added after fermentation in the bright tank in the form of cold brew coffee. Coffee beers are becoming more popular, and the coffee flavor is being added to both dark and light beers. The addition of coffee is mainly by coffee grounds, cold brew, and extract. The raw materials that are involved with this process include hops, barley, malt, yeast, cold brew coffee, and water. The main process equipment to design this process includes a grain mill, mash tun, kettle boiler, fermenters, bright tanks for conditioning, and the canning process, which will prepare the product for distribution. The final product cost was determined to be $6.46 per six-pack after accounting for all operating costs and the projected number of six-packs being produced per year. The product will be sold for $12 per six-pack based on analysis of other coffee-flavored stouts on the market. The United States is the second largest beer consumer in the world at 13% consumption. Even though there has been a decrease in the beer sales in the U.S., the craft beer sales have increased by 5%, specifically targeting microbreweries. The overall beer and malt market is over $111 billion, and the craft beer market accounts for 13% of overall market, which is about $26 billion. Microbreweries made up 22% of the production volume in 2017, which shows that craft beer market is rapidly expanding. The craft beer market is expected to obtain a compound annual growth rate of 14.1% from the years 2018 to 2023, which represents a high growth rate of the market and demand for craft beer. Based on 2017 statistics, there were 243 craft breweries in Florida, which produced over 1.4 million barrels per year. In the United States, Florida is the third highest in consumption of alcohol, with over 531,000 gallons consumed in 2017. Specifically in Florida, the Tampa Bay area accounts for 40% of Florida breweries. The brewery was decided to be located in Tampa, Florida due to the high demand for craft beer in the area. This graph represents the forecast of the beer production in Florida. A market analysis was done from the years 2005 to 2017, and a Monte Carlo simulation was done to predict the production rate for craft breweries from 2018 to 2030. This was done to justify the sizing that was decided on for our equipment design. The following slides will discuss the overall process of our brewery.
There are four main ingredients in beer: water, barley malt, yeast, and hops. Beer is categorized into two types: lagers and ales. The main difference between these two is in their fermenting temperatures. Lagers prefer a cool fermenting temperature around 40 degrees Fahrenheit, whereas ales like the warmer 60 to 70 degrees Fahrenheit. Qualitative differences are that ales are typically darker in color and carry notes of coffee, chocolate, or fruits. Lagers are bright in color and have more of a grain taste. The initial recipe used for the process was based on a 5-gallon batch and was scaled up to produce 10 barrels of beer. The ingredients include pale malt, flaked barley, black barley, hops, liquid yeast, and cold brew coffee. The liquid yeast was chosen due to the economic impact and more effective for the brew. Cold brew was chosen for the overwhelming coffee flavor that it provides. This is the block flow diagram of our process. It begins with milling the grain and sending it to the mash tun to be mixed with water. This mixture is then sent to the kettle boil where it's raised to 212 degrees Fahrenheit and hops are added. To prepare it for the fermenter, it is sent through a heat exchanger to cool to 60.5 degrees Fahrenheit. Yeast is then added and the beer is now fermented for 4 days. The CO2 that is released during this fermentation process is captured to carbonate the beer later on in the process. After the fermenter, the beer is then sent to the bright tank where the cold brew coffee is added. The beer will stay in the bright tank for 3 days to age the beer for flavor. From there, it is sent, carbonated, and canned for distribution. For the inputs of our process, we plan on using 455 pounds per year of coffee grounds, 388,000 pounds per year of barley, 6,800 pounds per year of hops, 19,000 pounds per year of yeast, and 255,000 gallons of water per year. We will be producing 243,000 gallons of beer per year, 400,000 pounds of mash per year, 16,000 pounds of wort per year, 19,000 pounds of yeast per year, and 8,100 gallons of wastewater per year. This is a table of our primary process equipment and their associated energy requirements to brew our beer. We start our brewing by milling the barley. This exposes the sugars within the grain and allowing them to dissolve in the water. The milled grain is then transported and mixed with water in the mash tun. At this point during the process, the liquid is called mash. Here, the grain is steeped for 30 minutes at 160 degrees Fahrenheit, allowing the optimal sugar extraction. Once the grain is steeped, the mash now becomes wort. The wort is then sent to the kettle boil, leaving some spent grain in the waste stream. In the kettle boil, the wort temperature is raised to a rolling boil of 212 degrees Fahrenheit. At minute 55 of this hour-long process, the hops are added. Adding the hops later on in the boil promotes a more aromatic effect rather than flavor. From here, the wort is sent through a plate heat exchanger to prepare it for fermentation. The wort needs to be cooled to create an adequate environment for the yeast to ferment. Also, cooling the beer allows for less risk of contamination. When the wort finishes transferring into the fermenter, yeast is added where it will ferment for 4 days. During the fermentation, the yeast cells will consume the dissolved sugars and generate ethanol and CO2. At the end of these 4 days, the wort has officially become beer. To promote for better taste profiles, the beer is then sent to the bright tank where it will age for 3 days at 37 degrees Fahrenheit. This is when cold brew coffee is added. If the coffee were to be added during mashing or boil, the oils would be extracted into the water, thus affecting the head and flavor of the beer in a negative way. Cold brew is highly concentrated coffee, and added when the beer is at a cold temperature would help negate the effects of these oils and thus providing a better flavor profile. After 3 days, the beer is filtered, and using the CO2 captured from the fermentation, the beer is carbonated, stored, canned, and shipped for delivery. This is the Gantt chart of our brew process. Brewing once a day with 30-minute transfer times between each stage in the process. Each brew stage includes 3 boils with 1 hour for transfer time and cleaning. This is for brewing 5 days a week for 52 weeks a year.
To optimize operating conditions and estimate the production of the fermentation process, a mathematical model from research literature was implemented into a MATLAB Simulink program. This model accounts for both the behavior of the yeast and the concentration of sugar and byproducts throughout the fermentation. Once the model was developed, an optimized temperature of 60.5 degrees Fahrenheit within a selected range of 55 to 75 degrees Fahrenheit was found to maximize ethanol production, while maintaining a reasonable batch time. This range was selected as temperatures below it produced fermentations that occurred too slowly, and temperatures above it produced large amounts of byproducts and could remove some of the flavor. Other initial conditions, such as initial yeast and sugar concentration in the fermenter, were estimated by values recommended by the literature. To find the optimal temperature within a range of 55 to 75 degrees Fahrenheit, the golden section method was applied to the program. This optimization method tests portions of the range and eliminates the sections that are suboptimal. With each iteration, it searches an increasingly narrow range until an optimal alcohol content is found within acceptable amounts of error. Columns A and D define the range the iteration is searching through, while B and C are potential optimal boundaries, the lower of which will be used for the next iteration. Shown here are the primary equations used in the fermentation model. The terms XA, XL, and XD represent the concentration of yeast cells in the active, lag, and dead phases, respectively. They are dependent on various temperature-dependent rate variables that determine the rate at which cells leave and enter the various phases throughout fermentation. Below these are the equations for concentrations of sugar, ethanol, and the two possible byproducts, diacetyl and ethyl acetate. These are dependent on the yeast cell concentration and other rate variables, such as those shown on the right. Shown on the right is the overall structure of the Simulink program, which utilizes the equations just shown as well as several temperature-dependent rate variables. The left diagram shows the input values used to model the initial conditions within the fermenter. Around 472 pounds of ethanol and 451 pounds of carbon dioxide are expected to be produced by the fermentation. As shown here, at 60.5 degrees Fahrenheit, a final alcohol by volume concentration of approximately 7.7% is obtained. Most of the initial sugar is consumed, with the final concentration being around 0.2 pounds per gallon.
A general rule of thumb for columns and vessels was used in calculating fermenter and bright tank size. This rule of thumb is height equals 3 times the diameter. After the fermenter model was obtained, all operating conditions and beer outcome will utilize this model. As stated earlier, the optimization temperature range was 55 to 75 degrees Fahrenheit. Again, the sugar concentration from the grains was 1.08 pounds per gallon. The heat capacities of hops and grains were assumed to be the same for energy calculations. While the grains are steeping to become wort, it is assumed that no malt or barley is actually transferred to the water. This simplifies the mass and energy balances. It is assumed that the city water does not have any major disturbances, therefore there is no need for any additional water treatment other than the reverse osmosis system. A 30-minute transfer time between equipment is assumed, and all equipment sizing was done for a 30-barrel batch. The quality of the coffee stout will allow this product to enter into the market above average production rates. Once again, all the feasibility calculations were done with a 30-barrel batch size. Percentage methods were used for working capital, overhead costs, marketing costs, distributing costs, maintenance, and salvage value. The tax rate was determined to be 26.5% for a corporation. This is 5.5% state tax and 21% federal tax. The pricing of equipment was determined using Towler capital cost estimations and vendor prices. It is assumed all operating costs will stay constant throughout the life of the project. The amount of water used was determined by doubling the amount of beer produced to account for cleaning and normal operation. Electric costs were determined by adding up all heat duties, pump power requirements, and the average energy consumption of warehouses per square foot. Finally, depreciation was assumed to be 7 years, and the MACRS depreciation model was utilized to maximize depreciation in the first years of operation. A production amount of 7,830 barrels per year was determined to be an above average entrance into the Florida craft beer market. This production amount accounted for 5 brew days a week, only weekdays, therefore operating 261 days a year, with a brewing batch size of 30 barrels per brew. The fermenter and bright tank size required is 30 barrels, with the mash tun and brew kettle being 10 barrels. This means that brew days will consist of 3 smaller batch brews to make 1 batch of beer. This will allow for more precise control of the wort and boil process. The equipment list is as follows. We have a grain mill, mash tun and kettle boiler, 5 fermenters, 5 bright tanks, plate heat exchanger, canning system, reverse osmosis water filtration system, water storage tank, carbon capture system, inline CO2 carbonator, glycol chiller, 6 pumps, and a beer storage tank, which all amounts to $656,000. The electricity consumption was again the total of the equipment heat requirements, pump power requirements, and average warehouse energy usage. This created a total of 156,000 kilowatt hours per year. This energy usage totaled to $16,000 per year. The water consumption for brewing amounted to 2,000 gallons per day, which took into account cleaning and brewing of beer. This amounted to 522,000 gallons and $2,300 per year. This design created a total equipment cost of $656,000, a raw material cost of $980,000 per year, a construction time of 2 years, an operating cost of $1.8 million per year, total capital investment of $5.6 million, a product value of $12 per 6-pack of beer. The return on investment, or ROI, was 25.23%. The net present worth was $1.31 million. The payback time was 4 years. The payback time cash flow was $1.75 million per year. And the DCFRR, or the discounted cash flow rate of return, was 24.3%. Here is the cumulative cash flow diagram showing the low, middle, and high product price per 6-pack. All expenses remain constant throughout each cash flow. The only change that occurs comes from the change in revenue. So our pessimistic cash flows were for 6-packs at $10. Our actual design ran at $12 per 6-pack, and then the optimistic design was for $15 a 6-pack. The chart of discrete yearly cash flows is as follows. This diagram shows the actual cash flows for every year. A 10-year life of the brewery with the 2-year construction period gives way to the 13 cash flows. Year 1 is the purchase of the land, Year 2 is 50% of the fixed capital investment, and Year 3 is the remainder of the fixed capital investment plus working capital. Year 3 corresponds to the start time of the brewery, or Year 0. Years 4 through 12 are regular operating years, and Year 13 includes the addition of working capital and salvage value of equipment, as this would be the end of the life of the brewery. A sensitivity analysis using a Strauss chart was conducted in order to visualize the effect of several variables on the net present worth. The raw material costs were varied from plus or minus 10%, the equipment price was varied plus or minus 5%, the product price was varied plus or minus 10%, and the attractive interest rate varied plus or minus 25%.
The primary source of impact of this process to the environment is in the form of carbon dioxide emissions. This comes from the fermenters and fuel for the brewery's energy needs. The CO2 separator captures the CO2 produced by the yeast, which will both provide a source of CO2 for product carbonation and reduce overall emissions. This production is about 120,000 pounds per year. The material impact from disposal of product containers can be minimized through use of recycled materials and biodegradable O-rings. Wastewater streams containing leftover solids from the process will be adjusted for pH before being sent to municipality for treatment. These include streams produced by the process that contain leftover wort and streams produced by cleaning the equipment. Spent grain and hops can be sold or even given away to local farms or businesses. There are several safety hazards within the process that should be considered.
production hazards include the movement of materials in the brewery via forklift. Safety precautions for this are to ensure drivers are driving safely and that they are certified to operate the forklifts. Chemical hazards include, but are not limited to, carbon dioxide in confined spaces, which can explode under high pressures and temperatures, the use of sodium hydroxide, which is very corrosive to the eyes, skin, and to metals, the use of sulfuric acid, which is corrosive to the skin and eyes, and the use of ethylene glycol, which can be toxic if inhaled or ingested. To treat the wastewater leaving the process, the pH needs to be checked before sending it out of the plant. If the water is too acidic, sodium hydroxide will be added, and if the water is too basic, sulfuric acid will be added. This will be done to reach the desired pH. A carbon dioxide monitor should be put in place to evaluate how much is being produced and when it could be safe to open the tank. Since there are many confined spaces in a brewing process, there should be an additional test done to evaluate the atmosphere inside any tanks before the operator enters. When working closely with all chemicals, proper personal protective equipment should be worn. Other major potential plant hazards include spills and explosions of equipment. This includes a batch of beer boiling over in the kettle boiler, or pressure building up in the kettle boiler, or fermenters. Also, dust from the grains around the grain mill could easily cause an explosion if ignited. All of these hazards could be detrimental to plant personnel. To prevent these from occurring, pressure relief valves would be in place as well as pressure sensors and temperature sensors. Also, the process controls design and standard operating procedures for the equipment and plant will reduce these safety hazards. All plant personnel should wear personal protective equipment that includes the following: work boots that protect against corrosive chemicals, hot fluids, and physical injury, such as crushing or ankle twisting, and that are slip resistant. Work clothes that cover the torso, legs, and arms with material that can reduce injuries from thermal, chemical, and physical hazards. Eye protection that reduces the likelihood of injury due to splashes, flying objects, and poking. Other protective clothing and equipment based on the tank task being performed. Examples include chemical protective apron, chemical or thermal protective gloves, hearing protection, and respiratory protection. The following slides will discuss the main product of our brewery, the Peak Coffee Stout. Shown here is the label for the Peak Coffee Stout. 5 of the main requirements for beer labels are the following. First is the alcohol by volume content, which would be 7.7%. Second are the health warnings, which are that alcoholic beverages should not be consumed during pregnancy, that alcoholic beverages impair your ability to drive a car and operate machinery, and that alcoholic beverages may cause health problems. Third, the net content of beer, which is 12 fluid ounces for a can. Fourth, the brand name, which would be Deja Brew. And fifth, the location that the beer is brewed in, which would be Tampa, Florida. Here we have started to market our product by creating a LinkedIn page and an email address for potential customers to contact us. Further marketing of the beer would include creating a website which customers could view and purchase our product. Further branding would include implementing the beer and brewery designs on t-shirts, stickers, and other small knickknacks. We would also like to create a catchphrase or slogan for our product. This design proposal is economically viable and profitable with a return of investment of 25%. This base process design can be used to develop a more diverse range of beer products. We recommend moving forward with initial purchases and implementation. We would like to note that to better understand this process, our team homebrewed a stout and added cold brew to it to mimic this product. Shown here is a demonstration of us brewing. We also toured Cigar City Brewing Company, one of Tampa's most famed microbreweries. Here are our references. We would like to thank and acknowledge Dr. Sunal and our teaching assistant, Kyle Cogswell, for assisting us in the development of this design project. We would also like to thank Eric Krieger for his professional help and information on the brewing process. Lastly, we would like to thank the University of South Florida's Department of Chemical Engineering.